All right, hi everybody. Welcome back to office hours. It's noon. We're gonna get started. We have a lot of cool things we're gonna talk about today. I think a lot of things that you guys will find pretty exciting. Hopefully it'll make a lot of real concrete sense to you and very little memorization. So you should be able to kind of do 1, 2, and 3 pretty decently at this point. So let's start with the nomenclature question where we're naming. So clearly we see this is no longer just a plain alkane, with substituents off of it. It's an alkene. More specifically, it's a triene. And we need to kind of adjust the name accordingly. So the first rule is, always find that longest parent chain. But now the little caveat this time is find the longest parent chain that includes every single alkene that you see. And we need to go through all of those pi bonds. Remember, we can't just start here and call, that 1. We have to go through the bond and call that 1, 2. Okay, so for me, I guess I would start on this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The reason why I went right to left this time was because I saw that alkene was terminal. It's all the way at the end. So I can number it from that end and give that alkene the highest priority or the lowest number, which is 1. Okay, so that's definitely why I started right to left. And 10 is definitely the longest chain that I see. So if I'm thinking about the substituents that I see along that parent chain, I see I have a methyl group, and it looks like I have one of those common names. And if you guys don't know that common name, that's sec-butyl. Okay, so remember, this is sec-butyl, which gets alphabetized by the B, and this is methyl. Okay. The other thing we have to think about is we don't really see any RNS geometry, but we definitely know that there's going to be EZ geometry going on. So let's classify any EZ geometry that we see. Okay, so remember what we said last class, that if that alkene doesn't have 4 different, substituents attached to, this carbon and this carbon, respectively, then we can't even say that there's EZ geometry because there's nothing to compare. So, being terminal, if we draw that horizontal line, through that alkene, we see we have a proton on the top and a proton on the bottom face of that horizontal line. Them being the same substituent doesn't give me any difference in priority. So there is no EZ geometry for that specific alkene. Okay, so let's try the alkene between 4 and 5. So if I were to draw, a horizontal line through here, and I were to number the substituents, clearly I have what looks like it's the sec-butyl group up top here, and then I have the I guess a alkene going on down here. So the question is, out of the sec-butyl and the alkene group, which one is better? Well, here we have carbon with carbon, carbon. So I'm thinking like C, C, and then there's an H there. Here I see C and then immediately 2 H's, okay? So clearly this one's better because I see that I have more carbons. So I'm gonna call that priority 1, this priority 2. And then this one's pretty easy on this side because we have a carbon chain versus a proton. So I would call this 1, and I would call that 2 as well. So the 1s being on the same side and the 2 being on the same side tells me that this is a Z or same side alkene, okay? And then what about the alkene between 9 and 8? Well, if I draw that horizontal line, I see I have, a carbon chain versus a proton, so clearly that's 1. And then this one is going to be either a methyl or an ethyl. Well, clearly the methyl is less than the ethyl, so I'm thinking this. So that gives me 1s on opposite sides and 2s on opposite sides. So this alkene that is labeled 8 and 9 is E. Okay, so we have none, Z, and E. So now I think we have enough information to put our name together. So remember, stereochemical information always goes in the front. So we're going to call this 4Z, 7E, okay? And we're going to say that there is sec-butyl on 4, so 4 sec-butyl, okay? And then 8, there's a methyl. Then there's 10 carbons, so that's dec. And then you have to say, you have to have the A right there, okay? Remember, when there's more than 1, you can't just say like, decene. You have to say like deca and then indicate the positions of those pi bonds and then finish the name. So we have to have the A, remember that when there's multiple. And then there's, what are the positions of these alkenes? 1, 4, 7. So 1, 4, 7. How many of them were there? Well, triene. Okay. So that is some crazy name. That's probably the hardest one you'd get. So 4Z, 7E, 4-sec-butyl 8-methyl, deca 147 triene. Okay, so that is really crazy. I feel like you guys should know how to do that at this point. Let's see, question. When do we not specify location of E and Z? When it's terminal, okay, like this example right here, when you have a terminal alkene, because you have 2 protons definitely going on, or any other situation where you have, you know, the same substituents on both sides. So, you know, down here, I could show you this depiction. There's no easy geometry there. Okay. There's also no easy geometry if I were to have that, because these 2 substituents are the same. Okay. Do EZ or RNS go first? Last time you said EZ, but Dr. H said that the lower number goes first. You also put RNS first on the worksheet. I don't really know what Dr. H does in her notes and stuff, but all I know is RNS like typically go before E and Z. Abby's saying EZ goes first. I've seen RNS before. What did we do last class? Didn't we do an example where it was RNS before? Yeah, I mean, I've always known that to be RNS geometry goes before E and Z geometry. Had E by itself. Yeah, it could have E by itself. That's possible. Yeah, so again, from just what I've been doing for 7 semesters, I've always had RNS before E and Z in the name. So I would do like an example like 5R, 3Z, you know, 6E, you know, something like that. What's Brian saying? Brian. I thought the last time you said easy, or at least that's what I wrote. On page 55, the last session you said easy before RNS. Maybe I'm just crazy. Let's see. It's definitely RNS, unless I just misspoke last time. Okay, avoid what I said. It's RNS before E and Z, and the way I can prove that to you is if you go to page, let's just go 56 in the workbook. You guys can see that, you know, when I got this edited, RNS is before E and Z. RNS is before E and Z. RNS is before any E and Z's. Okay, so sorry if I misspoke last time. I'm sorry about that. It's RNS. You can clearly see that before E and Z. RNS clearly before E and Z. Okay, are we all kind of clear on that at this point? Anybody else still confused? Good, great. Okay, sorry, I make mistakes sometimes. Lowest numbers of. Do you prioritize the lowest number of alkenes over longest carbon chain? When there is an alkylation like a vinyl instead of, okay, yeah, so Caroline, again, like I've never seen a naming question where you have had to say vinyl, like methylene, like any of those common names. This is the first semester I'm seeing that. I meant to ask Dr. Peterson. Let me do that right now, actually, once you guys are here. I'm texting her right now, one sec. Just so I don't forget. Okay, I just asked Dr. Peterson, so hopefully she'll respond to us while we're waiting here. And do you put sec-butyl in parentheses? No, I don't know why. You don't need to. Wait, do you say it's probably the lowest number of alkene versus one came? It cut out. Yeah, Caroline, I don't know. I just asked. I'm asking her. About that stuff. Sorry. You typically want to find both, like the longest carbon chain with the lowest priority. In terms of which one wins, I would imagine numbering the alkenes. Okay, numbering the alkenes. Yeah. Okay, let's keep moving. So on 2, which isomer is more stable? Is it E-but-2-ene or Z-but-2-ene? I don't even know what that is, but but I know is 4 carbons, and 2 there's probably an alkene, and it's E. So let's probably draw the E arrangement. 1, 2. Okay, so here's definitely where my pi bond is going to be. And remember that pi bond has to be E. So E. And then Z-but-2-ene is probably, okay, here's my pi bond, but it's Z. So something like that. Which one is more stable? And you guys should probably, you may not know this yet, but I feel like you guys can kind of rationalize which, yeah, Mary, thank you. Anybody else want to take a stab and just put in the chat box and guess E or Z? Okay, clearly I'm getting some E's. Yeah, so this one's definitely better, and the reason is someone put it in the chat box. Why? opposite sides, which also means trans, which also means, I'm looking for a word that starts with an S. It's always that classical argument. Anybody? Sterics. Okay, sterics. I like that. So sterics, if you have something 180 from something else, they are so far apart. Whereas these are kind of a little bit closer in proximity. So you can imagine a little bit of electrostatic repulsion with these kind of eclipsing electron clouds, a little bit more than this one would be. Okay, so definitely E, we love to be, E is more stable than the Z one. Okay, so definitely that one, E. Okay, so complete the reaction below, and we're going to talk a lot more about some specific things that we didn't discuss last time with this, but this is a hydrohalogenation reaction, the only one we've talked about so far. We've talked about the fact that, you know, these pi electrons are pretty nucleophilic, or they want some sort of proton or some sort of deficiency. And the reason that is remember, we drew that, you know, p orbital overlap that goes on. Change colors. That p orbital overlap that's going on, and we said it's located higher above the sigma framework. So we can imagine there's electrons in here, and they can, you know, grab some sort of deficiency. Remember, we have that electron cloud, this dipole moment towards the bromine, which makes that proton a little bit positive. And then we said, since the bromine's pretty electronegative, we're going to retain that electron density on the bromine. So the result was, you know, a carbon-hydrogen bond that formed from these pi electrons, but then we took electrons away from one of these centers, you know, from one of these carbon centers, and we made it deficient or positive. So we can kind of, you know, and we don't know all the details yet, but let's just say the carbon-hydrogen bond forms here on carbon, let's say 3, and then on carbon 2, since we took electrons away, we had a deficiency, a positive. And also, as a result of the mechanistic arrows we drew, we said we generated free bromide, okay? And the next common sense step would be to take that, you know, negative charge on the bromine, and then that's a nucleophile now, and attacks that deficient positive center, okay? And then we form a structure that looks like this. And again, we don't have to draw the protons in, but I just want to show it now. And also, we said we have to consider potential stereo centers that we generated. And we definitely generated a new chiral center. And we talked about the fact that these carbocations are unhybridized p orbitals. So remember, you can attack from the front face of that, which would form a wedge, or you could attack from the back face. So I'll call that A and I'll call this B. So this would be the structure from A, and this would be the structure from B. Okay, so that was a result of that mechanistic arrow. So we would always get this racemic mixture of products, you know, at the end of that reaction. Okay, so that's pretty much everything that we talked about last class. We definitely have a lot more details to talk about with this one, and we also have some other reactions we're going to get into today. How do you know where H and B are? Well, attached. You don't yet. I'm going to talk about that early right now. And the reason that is we didn't get to touch all the details that there is a rule for it. So you'll know in a few minutes. Ayan, why is this one and not the other one? Like, where is the plus in the other carbon? Yeah, exactly. I know this isn't, for you guys that are ahead and you guys that know this reaction in detail, you know I'm missing a couple of details, and that's because we didn't get to finish it all last class. But yeah, Marky Boy's rule. We're gonna get there. Yes, that's fine. Nice. Can we do either wedge reactions to racemic? Yeah, you would have. You would have to show both, if that's your question. You would have to show both of these. Okay, you need to show that you form both of those stereoisomers. Okay, so let's kind of talk a little bit more about this reaction and something called Markovnikov's rule. But before we do that, we're going to talk about something called carbocation stability, and that's going to give a little bit more detail on how this reaction progresses. Okay, so the first thing I want to talk about is carbocation stability. And the first trend, we're going to do a little bit of trend analysis. So we're going to talk about resonance. Okay, so resonance is back, and we're here to stay. So essentially, what's going on with this resonance stuff? So let's just do this example. We have, you know, maybe a structure that looks like that versus a structure that looks like that. Okay, so clearly we're looking at these two things, and which, you know, structure or which intermediate is more stable? And, you know, I'll give you guys a second. Let's say this is A. Let's say this is B. Which one? A or B in the chat box? Okay, Abby says A, Josh says A, Hal says A, John says A. Is A. Yeah, okay, so we're pretty much all consistent with A. And the rationale is the same rationale we saw when we did acid-base chemistry. Okay, remember when we said, let's subject this, maybe phenol, okay, let's subject this phenol to some sort of like aqueous base, like we said, like maybe sodium hydroxide. And the role of that aqueous base was to deprotonate that proton. We generated this conjugate base. I hope this is all still coming back. And we said that this was stable over, maybe this counterpart, this plain alcohol, because this negative charge was capable of being, delocalized or spread around a larger region of space. Okay, we could spread that over the molecule, and that was a good thing. Okay, so the same logic happens here. I can resonate, source to sink. Okay, so remember, still the same electron pushing rules, and then another resulting structure of that would be, that. So you can push the carbocation around. Remember, we used that lightning example, and I'll just draw that so you guys can remember the lightning example, that we don't like to have accumulation of charges. That's what the negative charges all up in the clouds are. And then it discharges to the positive ground, and then it kind of evenly distributes. The resulting structure would be, the cloud that is negative, positive, and then the ground is also a little bit negative and positive, negative, positive. So you have this equal distribution, okay? That's kind of the goal of lightning. The same thing with these resonance structures is we don't want to have one isolated positive carbocation. When we can spread it around, and maybe instead of it being +1, it's +0.5 and +0.5. Yeah, arguably. Okay, so resonance was the first thing we were talking about in terms of stability of this carbocation. And why am I even talking about stability in the first place? Well, let me tell you right now that you are going to get these intermediates in this reaction. You're also going to get this intermediate in other reactions we see later on in this chapter. So the stability of this structure actually is directly related to the rate of how fast this reaction is going to go. So you can rationalize that maybe a reaction that has this intermediate, which is lower in energy, more stable for this resonance argument that we've talked about. Since it's more stable, that reaction is going to go a lot faster than this reaction is going to go. Okay, so you can see why we have to talk about this thing. So resonance was our first trend. The next thing I want to talk about is induction. Okay, so we kind of heard about induction before. Okay, so let's take this example. So let me just do this one and a fluorine here versus, this one. So pretty simple. Okay, so we have this secondary carbocation with fluorine and the secondary carbocation alone. So, before in acid-base chemistry, we said, let's just do this kind of ring example, that if we had a fluorine and, I was like, circle out of, A or B, which structure is the most acidic? Okay, out of A or B, which structure is the most acidic? Put in the chat box. Oh boy, more acidic. Let's not forget acidic. Okay, remember, go back to the Stephen rules that I gave you guys. First thing you do, erase the H and draw a negative. Okay, then you ask yourself, how is that negative charge delocalized or spread or stabilized any sort of way? And we said, because of those inductive groups, yeah, I'm getting some more A's in there. With those inductive groups, we were able to spread that charge over a greater region of space. Remember that this negative charge was kind of pulled via the inductive effect towards that fluorine, and it was a version of charge spreading. Whereas here, once we deprotonated, we could not spread, okay? So in terms of acid-base chemistry, you're right. A was the reason, yes, induction is good. But now, that's actually a great thing that you just said that. But now it's bad. I love that. I love that. That was actually a great segue. Not anymore. You guys got it. But not anymore. So that's kind of like the very big take-home message here, is that in acid-base chemistry, induction was a good thing. But with carbocation stability, it's a bad thing. And let's kind of rationalize that, okay? So the exact same kind of logic is happening here, that this charge, whatever it is going to be spread towards that fluorine because it's inductive. But the difference here is that we already have an electron deficient center, okay? Remember, there's only 6 valence here. So now what we're doing with this inductive group is we're pulling even more electrons away from an already deficient center, okay? Does that make sense? It's already electron deficient with 6 valence electrons. And then we're gonna pull even more electrons away with this group. So now maybe let's say it's kind of like 4.3 0.3 maybe valence electrons. I'm just throwing out a number. 0.3, so we're making it even more deficient or even more charged, and that is not what we want, okay? So in terms of, carbocation stability, inductive groups are not good, okay? Okay, so yes, Mary, that's great. Positive with partial positive is bad, yes. Let's see, so Caroline, we're going back up. So that made A the weaker acid. No, A is the stronger acid because it's a more stable conjugate base, Caroline. And yeah, Hal, thank you for correcting. Claudia, does the stability of resonance outweigh the instability of induction and carbocations? It depends, Claudia. I have to see an example. We'll get into some of those where we have to rank them and we get multiple trends. She's already struggling to Mary, positive, partial positive, bad. Yeah, you got it. Okay, good. So far we've talked about a few trends. We've talked about resonance. Resonance is a good thing. Then we talked about, induction, okay? So that was a bad thing. Now we're going to talk about hyperconjugation, okay? So this is really cool. I've seen it before until I've gotten to organic before. So, Julia, so induction makes an acid stronger, but, okay, let me recalibrate you. So induction makes the acid, I shouldn't say that. So induction basically makes whatever that molecule is more acidic because the conjugate base is more stable, okay? That was back to acid-base chemistry. Now with carbocation stability, it's the opposite. Because we already have an electron deficient center, the inductive group makes it more unstable because we're pulling more electrons away from an already electron deficient center, and it makes it more charged, not charge spreading, if that makes sense. It makes it more charged, and it's not a good thing. Okay. The next thing we're going to talk about is hyperconjugation. And, something we didn't really talk about was, in Hal kind of alluded to this, I think that was him. Where does the H go and where does the bromine go? And the logic here is you can technically argue both. You said that the H could maybe, I've been showing the H going here and the bromine going there, or maybe the bromine going here and then the H going there. So let's just draw both. Okay, so let me say, what if I had that one and what if I had this one? Okay, so which one's the answer? Is the proton going to go here and the bromine going to go there, or is the bromine going to go here and the proton go there? And the answer in terms of real experimental yields, we're going to say we get approximately maybe like 80% and 20%, and I'm just like arbitrarily throwing those numbers out there. And the reason there's something that we have to talk about with why do we get more of that structure, more of this product than that one, okay? And it has to do with something called hyperconjugation and something we're going to talk about later called Markovnikov's rule. So in terms of hyperconjugation, what this means is when you form a carbocation, adjacent alkyl groups, and that basically just means adjacent carbon groups, can actually stabilize that deficiency. So what the hell does that mean? So let's just do the first mechanistic step. So essentially what I'm going to do is I'm going to, show this pi bond, this nucleophilic pi bond, grabbing that proton, and then that electron density between the hydrogen and the bromine is retained on the bromine. So the resulting structure is going to be a carbocation intermediate. And Hal, back to, I think this was your question, like the carbocation in this situation, we're going to talk about it with Markovnikov's rule, has to go on the more substitute side, okay? So let's kind of break into Markovnikov's rule right now. So there's this cool guy named Vladimir. I feel like all Russians' names are Vladimir. So his name is Vladimir Markovnikov, and back in, I think, the early 1900s, he decided to come up with this really cool rule that explained how to add these reagents to these alkenes. And it's called Markovnikov's rule. It basically says this. When given the choice, okay, so we're clearly given the choice in terms of position. When given the choice, we are going to add the hydrogen to the less substituted side, because then that's going to give us an intermediate with a carbocation on the more substituted side. Okay, I'll repeat that one more time. So what Markovnikov's rule says is, when given the choice, we're going to put the hydrogen on less substituted side, and that gives us the carbocation on more substituted side. And the reason why the carbocation goes on the more substituted side is something to do with hyperconjugation. Okay, enough of that with the words, and let's kind of prove it to you. Okay, so this is following Markovnikov's rule. This is the intermediate that I'm isolating, okay? And remember what I did was the hydrogen is going on the less substituted side, so that was here, okay? Because then when I pull the electrons away from it, it's going to give me an intermediate with the carbocation on the more substituted side. Is everybody kind of following me up until this point? So what hyperconjugation basically says is any of these adjacent groups, and I'm specifically looking here and here, any of those adjacent groups, so this methyl group or this other methyl group right here, can actually, the electron clouds of the CH3 groups can actually slightly lean in. Remember, they're all electrons, 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 electrons. Same thing here. These electrons in these adjacent alkyl groups can slightly bend over. Remember that these carbocations are unhybridized p orbitals, and these electrons can actually slightly lean into that unhybridized p orbitals, and you can stabilize that deficiency a little bit more. So now it's not like 6 valence, maybe it's at any given point 7 valence, maybe 6.8 valence. So do you see what I'm saying? These adjacent groups can stabilize that carbocation more. And then in terms of, ranking these, let's say I had, if I had to rank these molecules, in terms of increasing stability, where 3 is the most stable, okay, clearly this is 3, this is 2, and this is 1, and the logic there is hyperconjugation. For this, we're going to call this a tertiary carbocation, and we're calling it tertiary because there's these 3 groups attached, 1, 2, and 3. It's tertiary, and these 3 CH3 groups can all lean in and stabilize, potentially, that unhybridized p orbital, okay? But then when you look at this one that I ranked number 2, we only have now 2 groups that are capable of doing that. And then when I look at this one, we only have 1 group capable of doing that. So the more groups that you have adjacent to a carbocation, the more stable that's going to be, because you have a higher probability of any of those groups at any given point donating electrons into that deficiency. Okay, so now maybe this makes more sense why we're going to get this 80%, because we see we're going to form this intermediate where the hydrogen went on the more, the hydrogen went on the less substituted side, which forms a carbocation on the more substituted side. The alternative to that would have been the hydrogen going on the more substituted side and the carbocation going on the less substituted side. So does that make more sense now of why we don't get really a lot of this product? And the reason we don't get this product as much is because we get a primary carbocation where we have not as much hyperconjugation, but in this case where we follow Markovnikov's rule, we have more hyperconjugation. So again, we're going to go back to this logic where the more stable your intermediate or the more stable your carbocation, the faster that reaction can progress. So clearly we're going to go through this pathway and not through that pathway. And it's evident in the experimental yields that I showed. Okay. Let's take a breather for a second and let that digest, okay? In the meantime, people put your comments in the chat box. Let me know if you guys followed that logic with Markovnikov's rule / hyperconjugation. Oh, we love that. We love to see that. Yeah, that makes so much sense. Okay, good. I don't like saying dumbing it down, because that's kind of like saying that you guys are dumb, which you guys are not, obviously. So, it's just, I think I break it down to bare minimum. That's how we'll say it, the bare minimum you need to know. And you love this stuff. See, I like this stuff too. Yeah, I'm having fun too. Now you guys get it. When you understand organic chemistry, now you guys kind of understand me after a couple weeks, 6 weeks. When you understand organic chemistry, it really isn't so terrible. Like, it makes sense and it's actually enjoyable to do. So here, no, I love it when you dump it. Oh, you love it when you dump it down. Do you want to see a brief summary? It was kind of fast. Yeah, I can say it again. And how more substitute is the side with more carbons. Yes, the more substitute basically means the sides with the more branching. Okay, more substituents there, correct. And Caroline, I'll say it one more time. So with this hyperconjugation argument, we had a choice. Hal asked us at the very beginning, like, do I put the proton here or do I put the proton here? And how do I know? And we didn't talk about this last class on purpose. And this is something with Markovnikov's rule, which is really the underlying principle is hyperconjugation. That's why I kind of put it together. And what Markovnikov's rule says is when given the choice, meaning there's a lesser substituted side and a more substituted side, I am going to put the proton on the less substituted side. Well, why? Because then that's going to form a structure or an intermediate where the carbocation is on the more substituted side. Well, why do I want a carbocation on the more substituted side, like this one versus this one? And the reason that is we have hyperconjugation. Since there are more substituents, okay, on a carbocation with more substitutes, like I guess that's the point, carbocations on the more substituted side, you know, we have more substituents that are capable of donating their electron clouds slightly into this unhybridized p orbital, which stabilizes it a little bit. Whereas here, now we only have one group, so this one kind of chain, whereas here we have two chains. Two chains, anybody? No? Okay. And then here, we had three groups. So that's why we're gonna call this a tertiary carbocation. We're gonna call that a secondary carbocation because the two groups, 1, 2, oh well. And then here, primary carbocation, okay? I don't just do organic chemistry all day, I'm cultured. No, Abby, that's great. I want you guys to say that, actually. Do that. So you guys need to get in the habit of saying, oh, that's a tertiary carbocation. Oh, that's a secondary carbocation. Oh, that's primary. And you know, the more substituted your carbocations are, the more stable they are. It is really the same thing, but yes, definitely, Abby, that's great. Get in the habit of saying those terms, for sure. Okay, so let's move on. Oh, can you explain why you put bromine on carbon 2 and not 3 for question 3? Okay, why I put the bromine here? So, for warm-ups. Okay, so this was an example, like we don't have, okay, so great. Now that we're here, back to this question earlier. So I've been purposely giving you guys examples where we didn't have I don't know if you guys noticed this yesterday too, or on Monday, but I was giving you guys examples where we didn't have a difference in substitution on purpose because we didn't get to Markovnikov's rule yet. So both of these would be secondary positions, meaning if you look at that carbon, there's a group to the right, a group to the left. Here, there's a group to the left and a group to the right. So no matter where I put the carbocation, let's say it was here, or if I put it here, I basically had the secondary no matter what, and they're both stable, equally as stable in terms of hyperconjugation. We have this methyl group coming in, we have this propyl group coming in, here we have this ethyl group, and here we have an ethyl group. So in terms of stability of both of those intermediates, they were the same. And I only showed you guys one product, but the truth was in this situation, we actually had the product for this one as well. We also had that structure, but we weren't there yet. I wasn't. It does matter. It does matter, and you would get marked off if you didn't show this. We were just very early in our explanation of this reaction, and I wasn't ready to show that all to you yet. Okay, we have to kind of build. It does matter. So you would have to show them both in the exam, yes. And when we're now almost ready to do the predict the product questions in the workbook, and we're going to do those, and you guys will see where you're going to have to write multiple products. How am I going to know that? Yada, yada, yada. Okay? I promise we're getting there. Don't worry. So we talked about resonance. We've talked about induction. We've talked about hyperconjugation. And something I've always seen, it's kind of an obscure question that I want you guys to know. And it's still with the resonance. So I guess maybe resonance continued. I've seen this asked multiple times, and I wonder if it's going to come up. Which structure is more stable? Okay, let's call this A. Take a second. Let's call that B. You guys have the logic for this. Okay, so think about it. Think about what you know. We clearly are talking about resonance. Okay, and think about it. Stable means we're able to donate electrons into that deficiency and stabilize it. So what's different in between the two structures? A nitrogen versus an oxygen. So that should tell you a little bit something. Okay, I see some A's. Yes, if you said A, you're right. So think about what the difference between nitrogen and oxygen clearly is if they're in the same row, and that means that there's a difference in electronegativity. Oxygen is slightly more electronegative than the nitrogen. So, but that means that these lone pairs don't want to donate as much as maybe this one, and I'll emphasize it with 2 arrows. Since the nitrogen is less electronegative, nitrogen holds onto its valence electrons a little bit less, which means that those lone pairs are more likely to be donated with resonance, via resonance, to fix that deficiency. So A is more stable than B, okay? So I've seen this asked quite a lot recently in past semesters, knowing like when you have these cyclic structures. Okay, I think we've done enough with logic, and let's kind of just jump into practice problems. Hopefully that's good for you guys. Okay, so I am on page, okay, let's start with page 57, okay? Let's do a couple of ranking questions, okay? So I'm on 57, page 57. Okay, so we are right here. Lilas, what's your question? Because it's better to deal with the positive. It's just the sense that these lone pairs are more capable of being donated to fix the positive. That's how I would say it. Okay, so we're on 1A on page 57. So these are our structures. Because we have a couple trends going on here. Okay, so again, 4 we're going to say is the most stable. This is really important. Okay, this does not go away. This even comes up in Orgo 2 when, you know, you can have other reagents, and we'll see, that still form these intermediate structures, and that stability of these structures is really important in terms of writing the right product on your test. Okay, so in terms of stability, the first thing I do with these is I basically just write the classification. Okay, so basically what I'm going to say is this is a secondary carbocation, because I see I have one group here, another group there, and specifically I see there's resonance possible. So I'm going to say secondary, and I'm going to write RES to remind myself that that means there's resonance there. Here I see that I just have one group and two groups, so that's secondary. Here, what do you think? This is tertiary, right? One group, two groups, three groups. Here I see I have one group, don't be fooled, that's one, we're talking about carbon groups, one group and induction. So primary and then induction, okay? Oh, I think I drew that wrong. On the workbook, it's, yeah, I think it's, on the workbook, there's an extra carbon and then the fluorine. I just noticed that. So it should be secondary. My bad, I copied it down wrong. Okay, so secondary fluorine. So immediately, I can see that there's tertiary and secondary with resonance. So those two, like, okay, I like those. And then secondary versus secondary with induction. So clearly, this is the worst one, okay? For reasons we've talked about. Out of all of these, there's no primaries. Out of all of them, their secondaries is the worst. And then of the secondaries, this one is the worst because we have induction, where we're pulling electrons away from an already deficient center. So this is pretty bad. Then we're gonna go here. So this is the other secondary. Good, it's stable decently in the sense of hyperconjugation, but nothing else really. Then we have a tertiary. Okay, so I'm gonna call that 3. Hold on for a second, I'll explain that. I'm gonna call this one secondary with resonance 4. Okay. Test. Okay. The lower numbered carbocation with resonance is more stable than the higher carbocation without resonance. That probably makes absolutely no sense to you. Don't worry. So what does this mean? The lower number carbocation with resonance, meaning the secondary, okay? Secondary is the lower number when I'm comparing it to the tertiary, okay? And the, oh my God, I know. We had this example in this problem also last semester, and I'll clarify it in a second. So secondary with resonance, okay, versus a tertiary. And the test tip that I'm always gonna say is the lower number carbocation with resonance is secondary versus tertiary is more stable than the higher number carbocation, the tertiary without resonance, okay? And we always have this classical thing, 4 versus 3, and it's every semester it trips people up. And the truth is you saw this back with acid-base chemistry when I didn't tell you pKa's, like, they're probably pretty darn similar, like these two, because this one is partially stabilized in the sense that, you know, these 3 alkyl groups can slightly lean in and donate. But this one, some people argue is like, oh, you have the secondary, but you also have, instead of like it being partially leaning, here you have complete movement of electrons, like fully moving those electrons around, where these are just slightly bending in. So we always have that kind of argument. And I know the key says something different. I always say something different like than this. And the truth is like, Dr. Peterson would either pick a series of molecules that is very, very obvious, meaning like she would give you a tertiary and then a primary with resonance, not a secondary with resonance, so that it was pretty obvious that, you know, the primary with resonance is clearly less than the tertiary. Or she would give you some other sort of information, like an enthalpy number or something like that, to tell you something about the stability of this. So the truth is that 4 and 3 are probably equal in the sense that, like, they're both kind of could be 3. I know it's probably not the best example to do this for the first ranking question we have, but it's always this kind of questionable, like, which one is exactly the better one. So that's why the key says that's different. If you want to get, so yeah, so you can see, so 3 and 4 are just different. So it should be correct on the exam. Like I said, you probably wouldn't get, all you guys care about is what's on the exam. I get that. I honestly would say to you guys that you would have a better question on the exam. I wrote this, okay? So I'm sorry, I would say they're tied. Yeah, for all intents and purposes, they're tied here, okay? But in typical situations, this test tip rule applies. So what I'm saying is like, so something like this. Let's see, actually, let me do, actually, let's do this. Let's do, okay, so here's an example. Okay, this is where, like, this trend is better. So we have a primary, okay, with resonance, and then we have a secondary, okay? So the lower number carbocation with resonance, primary with resonance, is more stable than the higher carbocation without resonance. This one is more stable than that one, for sure, okay, because it can resonate, okay? So that's where this really, that tip really comes into play. The truth is you guys will get a better question where it's clearer on the test, okay? That's the truth. And you might get maybe, in the sense of, she might, by that I mean, she might give you 2 fluorines, you know what I'm saying? Your structures will be very clear, okay? I made this question, you know, I'm not a professor, so I don't always meet the mark on these questions. But let's try B, let's try another example, okay? Don't get so overwhelmed. So 1B, so we have fluorine, fluorine, fluorine. We have a carbocation there. We have this one here. We have this one. So a lot of these ranking questions will be easier. Okay, so here we are. So these are my, oops, and I dropped a carbocation somewhere. Here. Okay, so again, we want to classify. So we see we have secondary with induction. We have secondary with induction. We have secondary with induction. And we have secondary. Okay, winner immediately, right? You guys can obviously all see that. The one without induction is clearly the best. Then the ones with less induction, meaning less inductive groups, would be better. Okay, and then out of these 2 inductive, you know, molecules that look pretty similar, it's the placement of the carbocation that's different. And we said that, remember, this is the same thing back with acid-base chemistry. I remember I told you the refrigerator analogy. The closer you are to that refrigerator with the magnet, the more attracted you are. So you have more of an interaction when it's closer than it is farther away. So this is further, oops, my bad. Oh yeah, this is further away, and this is the worst one because it's close. So it should be 1, 3, 2, 4. Okay, so do you see what I'm saying? Like the ranking, like you'll get a better question. I really do wholeheartedly believe that for you guys. Like this is without a doubt very easy to rank. Hyperconjugation actually won't come into play here. It does, but it's not as much. And the reason that is because all of these structures are secondary. So all of those all these carbocations have at least 2 groups that can go in and stabilize that. And like Markovnikov's rule is not coming into play here because, oh, fine, actually you can say that. Let's say we had some sort of hydrohalogenation reaction. So like you basically would have an alkene here, an alkene here, an alkene here, an alkene here. And it's like, which one would be the fastest in the reaction? And it would clearly be this one because it's the most stable. Okay, so that's kind of how that's gonna, excuse me, that's kind of how that could be tied into Markovnikov's rule. Let's keep moving. I'm going to do all of these real quick. So let's do 1C. So we have, this is really important that you guys know this skill because it's like, I'm telling you, it does not go away. And we're going to do, we might go a little bit over today. We have a lot to cover, but up to you guys if you want to stay or not. Really up to you guys. Okay, so this is 1C. Again, first thing we want to do is classify. So secondary, and then there's pi bond is sufficiently close enough so that we can do resonance. This is secondary, but notice that that carbocation is pretty far away where we can't do resonance. Notice there's a proton here, so we can't really push those pi electrons over to that carbocation. So don't be fooled, just secondary. Here we have the tertiary, but we also have resonance possible. And then here we have secondary, no resonance. Remember that's that proton there, but induction. Okay, so that should be enough information to rank all of these. So clearly tertiary with resonance is the best. Secondary with resonance is probably the next best. Then just a plain secondary, and then secondary with induction. Okay, these are like the quality of questions I feel like you'll get on the test. I'm sorry about that first example. I know it's never a good thing. And solution for A, it's the, so I guess resonance wasn't included. For the first one we did? Yeah, so remember, it was just 3 and 4, which was flipped, and we said for all intents and purposes, we can assume that they're tied. It was a bad question, I think I wrote. I should have probably revised that for the 3rd edition. Okay, 1C. So it's pretty easy. Let me know if you have questions on that. 1D. So this is what I was talking about with knowing how to rationalize what those heteroatoms are going to do. Okay, Dr. Peterson loves this question, just saying. Okay, so again, rank these across the board. We see that we have a tertiary here, just plain tertiary. Here we have a plain tertiary, but with induction. Here we have a plain tertiary, but resonance is possible. And here we have tertiary also with resonance possible. And resonance is possible with these lone pairs on the heteroatoms. Okay, so yes, tertiary. What am I looking at something wrong? They're all tertiary. Abby, Caroline, which one are we looking at? Oh, I see. It doesn't, okay, so this is kind of tricky. It doesn't really, so it doesn't have to be an alkyl group, even though that's kind of like the classic example of hyperconjugation. It could be like any adjacent group that has electrons to share. And even though we don't, you're right, like I'm calling this, how about this? We call it tertiary-like. I like that better. Let's call it tertiary-like. And for all intents and purposes, you can consider it also a tertiary, okay? Because why am I calling it tertiary-like? It's as if there were 3 carbon groups detached. It's actually better than plain tertiaries because we have more electrons to donate, than a plain carbon chain. So yeah, you can call it tertiary-like because there are 3 3 electron-rich substituents attached. How about that? Is that good? Yeah, that's fair. That's a good question though. I like that. So in this situation, we said nitrogen is less electronegative, so that's the key. It's less electronegative, so it's more capable of donating those electrons in via resonance to, stabilize it. So 4, then 3, then 2, then 1. Okay. Caroline, so just not when it's in a correct. Yeah, that's great, Caroline, that's great. As long as there's no proton attached, or it's like not like another inductive group, like as long as it's not like a fluorine or a chlorine or something like that, then yeah, you can consider it a group that is capable of stabilizing that carbocation, or tertiary-like, like we said. Okay, 1D, 1E. All right, so we got a benzene question. Okay, benzene. So you guys can see why I was telling you guys that the first and second exams are the exams to get as many points as possible on, because clearly this material is a little bit more, I think it's easier. I like this stuff more. It makes more sense to me, but you can tell it definitely is a little bit more challenging than the other stuff from before. Okay, so again, classify. So this specific position, you know, when you're the carbon out, one carbon outside of the benzene ring, is known as the benzylic position, okay? Benzylic. And we're gonna do some reactions with the benzylic position, I think Orgo 2 or, oh, I really hope Dr. Peterson teaches Orgo 2 next semester so I can move up with you guys. Just ask her to teach Orgo 2. I haven't taught Orgo 2 in like 2 semesters, it's been a little bit. So yeah, ask her. I really want to move up. I haven't done Orgo 2 in a few semesters, so I'm kind of itching to get back into it. So just ask her to teach it. Anyway, so we have, this is a secondary, and we're going to call it benzylic. I don't know how I'd live without you. It's funny. Or the secondary benzylic, okay? And for all intents and purposes, we can just consider benzylic resonance. You can kind of arbitrarily call that resonance as well. I'm just training you guys like the monkeys that, you know, they say training monkeys. I'm training you guys because you want to start knowing that that's a benzylic position. Deadass, I love that. So this is a secondary benzylic, which basically means, you know, secondary resonance for our purposes right now, but get in the habit of doing secondary benzylic. Here, this is just plain secondary. It's too far away from the benzene ring to really do anything. So here, again, it can't really participate in the resonance with the benzene ring, but here it can actually interact with that ketone, and it's the inductive effect. And yes, I'll talk about that in a second, Caroline, one sec. So this is also secondary. Again, no interaction with that benzene ring in terms of resonance, but now we have like massive, and I'm gonna say massive induction, okay? Because you have 3 groups. So Caroline, great question. You can also, in this situation, call this allylic. So benzylic or allylic. So what are these terms mean? Allylic is specifically referring to this kind of fashion where you're one carbon removed from a pi bond. So, you know, you can't really see this in this kind of depiction of benzene. So let me scribble out the circle, but you can tell you're one position away from a pi bond. So this is the allylic position, but specifically when you're attached to a benzene ring, now you can understand why that might be called the benzylic position. So it's benzene plus allylic equals benzylic. Whoa. So yeah, so it's basically the same thing, okay? Just benzylic is a specific type of allylic. And those are some words you definitely should know. Yeah, definitely know benzylic and allylic. Okay, let's rank these. So secondary benzylic is probably my top one. Then my plain secondary is probably my next one. My secondary with some sort of induction is decent. And then my secondary with all of this induction, oh, that should be 2. And the secondary with all of this induction is probably the worst. Okay, so you can see, I think the first one was probably just a bad question, but B, C, D, and E were definitely pretty good. All right, I'm gonna leave 2 for you guys to do on your own. So let's kind of just talk about those directions for number 2 if you guys are looking along. So it says, don't look at the answers though. I have them circled. So provided below are pairs of molecules labeled A through D, and each pair decide which intermediate is more stable by circling it, okay? So you've been given all of these pairs, which I don't want to show because I don't want to give you the answers, and you have to rationalize, you know, which one is more stable. Actually, let's actually do that together. I said I don't want to do it, but I'm going to do it anyway. Okay, give me 1 second to pull it up on my computer. It's a fun thing. Orgo 1. Orgo 1s. And this is page what? 57. Okay. So Zoom, share with you guys this. Okay, so can you guys see that? Okay, let me try and zoom this somehow. Aha. Everyone good? Good, hopefully. Okay. Yeed, you're yeed. All right, so for A, okay, so let's for everyone, for consistency purposes, anything to the left of that dashed line is we'll call that structure 1, and anything to the right we'll call structure 2. So in the chat box, when we go through these, just say like 1 or 2. And so we're looking at A first, okay? So the first thing I see on structure 1, or the structure on the left, thank you, so sorry putting it in there, is I see this is a primary, but specifically this looks like a primary allylic or a primary with resonance, whatever you want to call it. And then the second one is just a secondary with no resonance. So this is that's the test tip strategy I was telling you. So now in the chat box, 1 versus 2, everybody. Okay, 1. Yeah, 1. So this is an example of where the lower carbon with resonance, or the lower carbon carbocation with resonance, is more stable than the higher carbon carbocation, meaning more substituted, without resonance. Okay, so definitely structure 1. So for P, we have an epoxide, okay, and it looks like that secondary position is where that carbocation is. But don't be fooled, that oxygen is too far away for any resonance to be, happening. Okay, remember there's a proton right in here on a dash, so you can't really resonate down. Here we have a carbocation with looks like a lot of resonance, and remember this substituent, back to acid-base chemistry, is an electron donating group. We have lone pairs on top of here, and we add more electrons into this ring. So that should be enough. Structure 1 or structure 2, which one is more stable? Yep, 2, love that. More stable intermediate. Right? C. Okay, so it looks like we have a primary allylic again versus a secondary, and it's not allylic, that's secondary inductive. Okay, so 1 or 2, guys, for C. Yep, 1. Awesome. You just got it. Okay, let's move on to D. So for D, we have either secondary or we have tertiary. Okay, 1 or 2. 2. You guys got it. All right, so I think you guys are pretty good on carbocation stability, which is a huge, massive skill to understand, which is important. If it's easy to you, great. It should be easy. But a lot of kids struggle with this, and it's like a huge area of like confusion moving on past Orgo 1 and stuff. Okay, let's do 1 question. So I actually gave you, can I go over A again? Yeah, so this was that test tip strategy I was telling you. So the lower, can you guys see me? Oops. We're back. Okay, the lower number carbocation with resonance is more stable than the higher carbon carbocation without resonance. So that example was down here. We had a primary with resonance versus a plain secondary without resonance. And we said that, the secondary is better in terms of hyperconjugation, but this one is better in the sense that it has resonance. So which one wins? And the answer is this one, because of the fact that it resonates. And that was kind of the same example, and let me share my screen again. The same example we saw it with A, we saw that this was a primary with resonance, and this was just a plain secondary, okay? Which is basically like what I said right here. Got it, good. Okay, so I don't know if any of you guys remember, but I said, back when we were doing resonance in the very beginning, I gave you this problem, and I was like, we don't really know how to determine major contributor, and I give this problem every semester on purpose at this point, with the intent of coming back to it right now. So you probably don't remember it, but we are on 3 on page 58, okay? So we're here. And the instructions are to draw basically the 2 other contributing structures, and then identify which one is the major contributor. And at the time, you guys didn't know how to identify which one was the major contributor because you didn't know carbocation stability. But clearly something's going to happen with these pi electrons that maybe changes the placement of that carbocation around the ring, and then that's going to give me a different answer, okay? Also, real quick, I think this is worth showing. Hold on. 1 sec, guys. I want to show you all my cat. He just started looking at me, and he's really cute today. So here, I'll show you. Do you guys see me? And then this is my cat. He's so cute. He's 6 months. He just turned 6 months. Yeah. Anybody cares? It's cute. Yeah. So let's go back to this question. So I love him. You guys love him. Yay. Yeah. He was found at the Gainesville airport. And when I found that out, I had to adopt him. So he was found just walking like the tarmac. And I was like, someone needs to take him. So we took him. He's a cute guy. All right. Anyway, I love that. You guys are funny. King. All right. So the first thing you remember is source to sink. Okay. So we see we have a source of electrons, and we're going to go to a sink. Okay. So source to sink. All right. So then that means, and we do 1 move at a time. Remember all those rules that apply. So if I took electrons away from that carbon, I am now deficient there. Okay, is everybody clear on these? I'm assuming you guys are good at resonance by this point. And then do 1 more move. Oh, okay, and then we're here. Okay. So clearly, I think the resonance isn't the issue. I think the issue was determining major contributor back then. Okay, so now when you look at these three structures, 1 versus 2 versus 3, which one is the major contributor? All right, I see 3. I see 3. Yep, 3, 3, 3. And the reason that is we have primary allylic, basically, primary allylic. Here we have secondary allylic, or secondary with resonance, whatever you want to call it. And this is tertiary allylic. Okay, so now you have enough information to determine major contributor when it's not, you know, one of those things like certain, like conserving octets or I don't even know what else there was, like resonance or things like that. This is pretty obvious now with carbocation stability. Okay, so same thing applies. Just want to bring back some old things. And now we're going to go to question 4. So question 4, I'm going to share my screen. I know we're at 1 o'clock. So if you guys can stay, you know, maybe like another 10, 15 minutes, like it'll be worth it. If not, like just wait for this to come out on YouTube. But we're going to go back to the workbook here online, and we are now here. So this is kind of going into Markovnikov's rule. So I don't know why it keeps doing this glitchy thing. 1 second, guys. Let me zoom out and, oh, there's another page. That's why. Okay, so we're here. So we're there. So the question here, ignore the top. It basically says is imagine taking these alkenes and so I want another hour. Yeah, it's free tutoring. Honestly, it's good. So basically, imagine taking all of these alkenes and then you're going to throw them at some sort of, you know, hydrohalogen. So in this case, we're talking hydrobromic acid. That's what we see up top here. Okay, let me annotate. So draw. How do I draw? Okay. Hydrobromic acid. Okay, hopefully you guys can see that. So hydrobromic gases are imagining basically doing those reaction schemes. And what all you want to do is identify the more or less substituted side, because this is setting you up for Markovnikov's rule. If you can identify really quickly which side of that alkene is the more substituted side, immediately you're going to put a carbocation in there. If you can immediately identify the less substituted side, that's where the hydrogen goes. Okay, so quickly, out of, you know, this left side or the right side, you know, what is going in this box? M, L, or I? M. Great. Okay. It's more substituted. Okay. Oh, that's too thick, I think. It's M. Okay. Yeah, I like that. M, because we see we have this isopropyl group, this methyl group, and then this right, you know, rest of the fragment. Then over here, that makes that the less substituted side. So what you can really basically just do is count groups. So 1, 2, 3. So you can call that the tertiary side. And you can call this side the secondary side. Okay, so on the secondary side so Markovnikov's rule basically says when we're subjecting these alkenes to hydrobromic acid or hydrochloric acid or hydroiodic acid, any of those things, the hydrogen is going to add to that less substituted side, and that carbocation is going to form on the more substituted side. Now that should make sense of why that carbocation is on the more substituted side, because of hyperconjugation. How? So the sides you're talking about earlier are the sides of the double bond. Yes, that's what I was talking about. So this question should make it as clear as possible from earlier. Okay, so that was that one. Let's clear and move on. So here, you know, in terms of, you know, the left box and the right box, what goes in the left box? More. Yeah, this is definitely the more substituted side. And if I were to put a number, what would be the number? Like primary, secondary, tertiary, what do we think? Secondary. Yeah, secondary for sure. So this can also be called secondary, whatever you want. Here is less, and here is the primary. Okay. Do you see what we're doing? Nothing really crazy here, but this is like very important. Like I added this question on purpose so that you guys can like build and see where this comes from in terms of Markovnikov's rule. Okay, so that's that one. And now I think we'll try C real quick. So now if you were thinking about, this one's a little bit trickier, so take a second. Don't just be so quick to answer. What goes in this left box? M, L, or I? I, good. Okay, so this should be identical. You can see that both of these are actually identical. Okay, I. And what's happening is here, we have a secondary carbon because we see we have, you know, something to the right, left, something to the right. Here we also have a secondary position. So something to the left and something to the right. So this is the situation where we're talking, this is the warm-up question. I put this one as a warm-up question where, you know, now let's do an example of like predicting the product. Can you see my paper hopefully still? So if you had this on a test, okay? If you had this on the test, what you would do is this would grab that, okay? And then that would generate the free bromide, okay? So now, since that both of those positions are secondaries, you get two intermediates, okay? You get the carbocation here, and you also get the carbocation there. So and the reason that is they're both equally as stable, so they both equally form. 50% this, 50% that, okay? And then the bromine comes in and attacks there, racemically, and also attacks there. So you actually get 4 answers, and you would have to put 4 answers on the test. Okay, because when there's not a difference in, a substitution, we get a mixture of products like this. So actually, this might be, no, this isn't symmetrical. Okay, so that's a situation where you get all of these products because they're identical. But typically, we're not going to have that situation. We're going to move on to question 5, and we're going to see the example of that right now, okay? Okay, any questions on why C was a little bit different, okay? Knowing that it's both identical? All right, let's go back to the paper. Cool. Yep, all 4 products and 2 intermediates. Yep, in this situation, you have all of those. So 25%, 25%, 25, 25. Okay, so we're gonna go back to, oh, I lost my questions, but there you go. Okay, so first thing is, so this is now, a big picture of everything together. So this is with Markovnikov's rule, this is with carbocation stability. Now you guys are really ready to answer all these questions. Okay, so first mechanistic arrow is going to be nucleophilic pi bond, proton, you generate free bromide anion. Now, according to Markovnikov's rule, this proton goes to that secondary position and the carbocation forms on the tertiary position. So I'm going to draw this in only now just to show you that that's where the hydrogen went. Okay, then free bromide comes in and attacks at that position. So we get this structure. Did I generate a chiral center? No. So this is your only answer. Okay, so that's why we spend so much time talking about chirality and enantiomers and diastereomers, is because you have to do that with your products. Like in this situation there wasn't any, so we're good. But you have to know that that wasn't a chiral center to have realized that you only have one product here. So the chirality stuff does not go away. That's why I said it was kind of troubling that the average was so low, but I don't think that's you guys. I don't think that pertains to you guys since you guys are all here. Yeah, exactly, Madison, that works. The highest energy intermediate is the least stable. And this is the lower energy intermediate, meaning the most stable, because we have a tertiary carbocation instead of secondary carbocation. However, I think if you're looking at the directions, and I think that's where you're confused, Madison. High energy intermediate is just a phrase used to refer to intermediates, period. Since they're charged compared to these neutral molecules, they're just considered higher in energy. But yeah. Is there ever a curve on the test? We're not going to curve the test, but I'm a little nervous about saying this out loud, but whatever, even though, whatever. It's always pretty much gets curved at the end of the semester. Like the grade cutoffs always pretty much change a few points up and down every kind of cutoff. So you can pretty much guarantee, even though I'm not the teacher, you can pretty much guarantee that it's probably gonna go up and down a few points. I think the A went down, I think 2 points, and expanded that range a little bit. So yeah, at the end it will get curved. Okay, let me keep moving. So that's that one. So let's move on to B. So we have, this, HCl. Okay, so same types of things going on here, formulates here. So we're going to generate this secondary carbocation, not the primary one, because that follows Markovnikov's rule. Chlorine is going to come in and attack. So we get chlorine. Did I generate a chiral center? Yes, I did. So I need to account for, and I'm drawing this really fast, both of those. So you need to draw both of those. And you need to know that that's enantiomers. I have a high C now. Should I be worried? Sabrina says, what? I'll go over that one again, Sabrina. John, no, do not be worried. I think you definitely need to get as much help as you can in terms of like knowing every single thing that we're talking about in these sessions. But I don't think, we're never going to give you an exam that's impossible. You know what I mean? So it's, if you learn it and you really understand it and it is doable to learn it, like I think you can totally pull it out for the next 2 exams. I scored the highest on exams 3 and 4. I did worse on exams 1 and 2 because I don't like that stuff. I like this stuff better, but that's just me. Okay. Sabrina, are you confused on this? Okay, get back to me if you do. Yeah, on the chiral part. Well, it's a chiral center, so we have benzene to the left, methyl to the right, chlorine up, and a hydrogen back here. So that's 4 different groups. We generate a chiral center, and yeah. Yeah, okay. Yeah, John, that's how I felt. I really did better in the second half of the class, and I think you will too. Good, Sabrina, I'm glad you're good. Mary, wait, can you please explain the high energy thing? Okay. It's really not, I think you guys are reading a little bit, not this. I think this is a situation of overthinking. High energy intermediate is just a phrase referring to any intermediate in the entire universe. Like intermediates by their nature are high in energy compared to these neutral things. Like it's just, this is charged, these are not. So by proxy, intermediates, this whole middle column, are always just higher in energy than your reactants and your products. Now, when we refer to energy with the intermediate specifically, when we have that choice, like this, like for this, let's take this molecule for this one versus, so we have the secondary versus the primary. This is higher in energy compared to this one, okay? Because this one is more unstable because it's primary. So they're both considered high energy intermediates, just one is higher than the other. So yeah, Mary, I think that just comes down to an overthinking thing. You're just overthinking directions, when in actuality, it's just like that higher energy intermediate just refers to draw the intermediate. Just to make sure the carbon goes with the more subs, yes. So the correct answer for this one is that. Okay. So that is enough that I want to do for you guys today. To see on your own. We still have one more little thing to talk about with carbocation arrangements. My guess is, did you guys do multiple reactions yet, or you still are kind of on hydrohalogenation? Did you guys do acid catalyzed hydration, stuff like that yet, or no? Not yet. Great. Okay. So this is a lot of information, especially the first week after your exam. So stop here. I would basically say you guys should stop up into, well, we didn't do rearrangements. You can't really go that far in the workbook. I would basically just, you can do on page 63, 11D and 11E. Other than that, you're probably gonna have to wait for me to keep going, but that's good. Just make sure, go over all the other pages already that we've already talked about. Make sure you kind of know all the information so far. And then we're gonna pick up with carbocation rearrangements on Monday. So we'll finish that. And then I think we'll also have enough time to talk about some extra reactions that you guys will cover maybe Friday. Okay, so with that, good luck guys. Hopefully it's getting better and you're enjoying this kind of rainy, gloomy day. And vote, don't forget to vote. Rights Union, do that. Bye guys.